Now that we have talked about quadratics, we can kind of move on to some of the basics of polynomials. We're going to spend all of next week looking at different ways to understand polynomials. Today's second half of the lecture, my guesses will be a little bit on the shorter side, but one of the byproducts of being an asynchronous course is some weeks end up being a little bit busier than others. So now it's time to properly define a polynomial. We've written the form of it a few times, but let's fully explore this definition. So a polynomial and we say that it's of degree n, or of order n sometimes, is a function of the form p of x, and obviously you can use whatever letter you want here, but it's p of x is a n x to the n plus a n minus 1 x to the n minus 1 plus, and all of those, a1x plus a0, okay? And defining a couple of these things, we have n is a non-negative integer. We have that the numbers, right, all of these a sub whatever are real numbers. So the numbers a0, a1, all the way up to an. Those are called the coefficients. A0 is the constant coefficient. An we call the leading coefficient. And as a sort of byproduct of this, the term a1 x to the n is the leading term, okay? Sometimes it's also called the controlling term. We will sort of see why later in this lecture. So I'm going to jot down a couple of examples for you, right? We might have, say, 2x to the 5th minus 3x squared plus 4x minus 2. Let's do these in a bunch of colors. Why not? We might have x squared plus 1. We can get weird with our terms. We could have pi x to the 18th minus 3x squared. I don't know, say plus pi squared x minus 4. Or let's do one more. Say p of x is just minus x to the 5th, right? And sort of labeling these really quick, I guess we'll do this in black. 2 is our leading coefficient, right? This polynomial is of degree 5, right? Because we have an x to the 5th is our highest, right? And then we have a constant term of negative 2, right? Similarly, with this green function, there's a phantom 1 is our leading coefficient. We have a degree of 2 and a constant term 1. The leading coefficient of this orange one would be pi. It's a degree 18 with constant term minus 4. And then finally, this purple guy, the leading coefficient is negative 1, right? It's a degree 5 polynomial, and the constant term or constant coefficient is 0. Okay, fairly simple stuff there, right? And we're going to start looking at graphs. Graphs will come into a much bigger play next week as we start looking at how to graph them. But let's review some of the parent graphs, right, for these power functions, right? Because these are just a sum of individual power functions. So, I don't know, let's review, let's say the first 4. So we have, I can't fit all of them if I keep them right on the grid. Sure, that fits. You know, we might have x squared, which looks like a parabola because it is a parabola. X cubed is going to look like a cubic function, something like that. X to the 4th is not a parabola, but it does sort of resemble one. It's going to come in and it's going to hug the x-axis a lot more. And then x to the 5th is going to do something similar to a cubic, but as we said, it hugs the x-axis like that just a little bit more, okay? So let's do a couple of examples of this, right? Let's say graph, we'll start with A, let's say f of x is negative x cubed, right? When we graph this, what we're going to do is we're going to take our graph of x cubed and we're going to invert it along the y-axis, right? We're going to flip it this way. So we're going to kind of grab maybe 3 of our key points, right? You know, we can grab these 3 key points here, right? Which is going to be the origin, which is still 0. On the regular cubic, we're at +1 at 1. So on the negative, we're going negative, and the reverse is true there. Since we're just interested in a sketch here, right? At positive -2, it would be, you know, 8 and -8. It would be, you know, around 8 and -8. We're not going to add in those points. Just going to show that the graph gets very large, whether it's getting large in a positive direction or large in a negative direction. Going to our next one, let's say g of x is x minus 3 to the 4th. This is going to consist of taking our graph of x to the 4th and moving it 3 units, so we can count 1, 2, 3. We know it's going to go up 1 on 1 step, and in this case it would go up 16 on 2 steps, and that 16 is well beyond the scope of this kind of graph, so we can just, you know, get the idea of it. Since this is a quartic and not a quadratic, right, it's going to hug closer to that x-axis, and it might look like that. And then we'll do one more. We'll say -2 times, say, x plus 2 to the 5th plus 3. Right, so, you know, throw down about what our axes are going to look like. Since this is a 5th degree polynomial that we're sort of taking as our parent graph, it's not going to have a vertex per se, but the origin, right, what would have been the origin is going to go to -2, +3, right? So our new origin is here. And then we can draw, you know, -2 x to the 5th starting here. My 1 step in either direction is going to take me to 2. The y-intercept of this guy, if you were to expand it out, I believe is -13, which means that our graph is going to be very steep. But if you recall, since it's a 5th degree, it's going to kind of hug this line as it gets closer. And it's going to do something like that, okay? So the graphs of our polynomials of degree 0, 1, and 2, they're fairly simple, right? They're a quadratic, they're um, a line, they're even like a flat line, right? Um, but our general polynomials can get strange, right? You might have a polynomial that has behavior like that, okay? Much, much more complicated than um, what we have been looking at previously. But there's two things which all polynomial graphs have, right? No matter how complex your polynomial, you could have a 100-degree polynomial, but it's always going to have two properties, okay? And that's that polynomials are always, one, continuous. We talked about that first about 2 weeks ago. Continuity is that you can draw it without picking up your pencil, right? So say here's the graph of a function which is not continuous, right? You might have something that does something like this, right? This has a hole here, which means it can't be continuous, and it has a jump here, which means it can't be continuous, right? Continuous functions can be drawn without picking up your pen or pencil. The other big property that polynomials have that these other sorts of functions don't is that every polynomial is smooth. And what smoothness means is that, it is pretty much exactly what you would think it is, right? You can draw it smoothly without any sharp turns or corners or anything like that, right? So let me give you, another non-example. So the function that I'm drawing right now, right? This function is continuous. I was able to draw it without picking up my pen, but right here and right here, we have these sharp turns. And at these sharp turns, my pencil is kind of going one way, and then all of a sudden, the direction that it's moving changes, very, very steeply, so steeply that we get sort of a jump in the direction that I'm moving, right? Um, and so all polynomials are always both smooth and continuous, right? So you might have a polynomial that looks like this, right? Smooth and continuous. You could have a polynomial that looks like this. Maybe it comes up, it goes down, it might go up a lot, right? But as long as like the way that it turns around here is done so smoothly, it's a polynomial. So these are polynomials, and these are not, right? This one is not continuous, and this one is not smooth, okay? So the next thing that I want to do is introduce a little bit of notation to you, okay? And this new notation should sort of make intuitive sense, and it's this statement right here, right? X goes to infinity, right? That's how we say this, right? We say x goes to infinity. And similarly, we might have something like this, right? Which we would say x goes to negative infinity, right? And what this means right, is that x increases without bound, right? There's no bound to how we're considering x. We're considering x, as larger than 10,000. X is larger than 10,000 into 10,000, right? Um, that's what we're talking about, right? We're saying however big you want, x goes past that, or however small, or however negative you want. X gets more negative than that, right? X increases without bound is this guy, and x decreases without bound is this guy, okay? And we're going to look at how we can use these to study some of our polynomials. And we're first going to do that by looking at two polynomials that we know fairly well, okay? So say f of x is x squared, okay? So we'll ask, what is the behavior of the graph of f as x goes to infinity, right? What about as x goes to negative infinity? And hopefully this will make a little bit of sense to you guys, since we've been graphing these for a bit, right? Let's take your favorite quadratic, x squared, okay? So what happens, so the question is, what is the graph doing as x increases without bound? Well, as x increases without bound, you're going to square it, so it's going to be even bigger, right? So we can say as x goes to infinity, our output variable on this is y, right? So as x goes to infinity, y goes to infinity. That's the behavior of the graph. Similarly, what happens as x goes to negative infinity? Well, when we go really far this way, get some very, very negative number, negative 100 million, square that, we're going to get positive 100 million squared, right? So as x goes to negative infinity, it would seem like y also goes to positive infinity, okay? So that's fairly standard. We'll do one more like this. We'll say, what about, say, g of x equals x cubed? We'll jot down a little graph. We'll jot down a little graph of this situation, just to remind ourselves, okay? And we know that the cubic looks something like that, right? And just looking at this, right, the behavior of our first statement is the same. As we go this way, our graph is going to continue vertically upward, right? So as x goes to infinity, y goes to infinity. Easy enough. But what about as x goes to negative infinity? Is it the same as x squared? Well, let's take a look, right? As we put in more and more negative inputs, our output is still negative, right? That's the thing about cubing. When you cube that -1 that's sort of in front of whatever, you still end up with a -1. So unlike x squared, for x cubed, as x goes to negative infinity, y also goes to negative infinity, okay? So now the question is, what about general polynomials? Right? What is the end behavior, right? The behavior as we get really, really large of, say, p of x equals an x to the n plus an minus 1 x to the n minus 1. And then I'm actually going to leave off the linear term because it's there in the dot, dot, dot. Well, it turns out, and I'm going to walk you through the idea behind this in a second, that the end behavior of some polynomial p of x is determined solely by two things, okay? So it's determined by A, the degree of the polynomial, and the sign of A sub n, okay? And I want to give you a little example to sort of illustrate this, okay? Say we have this function, right? Say f of x is x to the fifth plus x to the fourth plus x cubed, okay? What happens if we put something really big in here, right? Because we're considering arbitrarily large values of x. So what about, say, I don't know, what's f of like 10 to the 10, right? Some just gigantically large number, okay? Well, that's going to come out, looks like 10 to the 50 plus 10 to the 40 plus 10 to the 30, okay? Now, all of these are large numbers, right? 10 to the 30, gigantic. 10 to the 50, also gigantic. But one of the things about dealing with these orders of magnitude, right, is yes, 10 to the 40 is a large number, but compared to 10 to the 50, it's nothing. 10 to the 50 is so much larger than 10 to the 40 and 10 to the 30 that these two honestly might not, that relative to 10 to the 50, these two are basically meaningless, right? 10 to the 50 is just so much bigger, okay? You know, even if the coefficient here was astronomically huge, well, x is increasing without bounds, so I can keep increasing it, and eventually this term, right, the term with the highest degree, is going to take over, right? And it won't matter what the other terms are. For our end behaviors, things get arbitrarily large, that's what's going to take over. You know, we could have, you know, it might do whatever in the middle here, who knows, right? But as x gets really, really large, we're going to be following something like an x to the fifth curve, right? And that's what analyzing end behavior is all about. It's looking for, you know, it's saying like, okay, I don't know what's going to happen in the middle. We can look at that later. What's happening as my graph gets very, very large or very, very negative? And as I said, it's determined by the degree and the sign, and it actually has to do with whether or not the degree is odd or even. And then the sign can be positive or negative. So that breaks us into 4 cases. Okay. So then that means we'll need 4 graphs. How about these 4 graphs, right? And we'll break this into our, you know, 2 sign case, or we'll break our first 2 cases up like this. Let's say p of x is odd, or these two, and p of x is even on those. And then across the columns, we'll say maybe a sub n is greater than 0 and a sub n is less than 0. Okay. So again, looking at this, say we have an odd degree function with a positive number for the leading coefficient, right? We know that the general like base form of an odd degree follows something like this, right? Now, we don't know what's going to be happening here, but since that odd leading term is our controlling term, we know that it's going to do this, right? It can do whatever you want in here, but our end behavior is that way. Writing that right here, you know, as x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to negative infinity. If our leading coefficient is negative, we're going to get the same behavior, just with it reversed, right? We might have something like this, you know. We know it's going to continue up and to the left, and then it's going to do something as we go this way, and then it's going to go down and to the right. To write this analytically, as x goes to infinity, y is going to go to negative infinity, and as x goes to negative infinity, y is going to positive infinity. Even functions tell a similar story, right? We know that if we just looked at the controlling term of an even function, it would look like this if the leading coefficient is positive, okay? And we can't guarantee that those middle terms aren't going to mess up the middle, but they can't mess up the end because x is getting arbitrarily large, which means my graph is going to have this form. It's going to continue up and to the left. You know, it might come down, it might do something fun. I don't know, maybe something like that. Then it's going to continue up and to the right. So as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y goes to positive infinity, right? That's what these arrows out here mean, okay? And then final one, just as we saw before, if our leading coefficient is now negative, we're going to flip it vertically, right? So it's gonna, maybe do something like this. Who knows what the exact behavior is? We'll look at that soon. But it might look a little something like that, where we have as x goes to infinity, y will go to negative infinity, and as x goes to negative infinity, y would also go to negative infinity, okay? I have two quick examples for you of this kind of processes, right? So we'll say state the end behavior of the following functions, okay? We'll say our first one is maybe p of x is negative 3 x to the fourth plus maybe 5x cubed plus 100x squared minus 2, right? Again, it doesn't matter how big these terms are or even how small this term is. As we're looking at the end behavior, this term is going to take over, and this term is negative, right? Which means graphically, we're going to eventually be doing that, right? So that would mean when we're looking at end behavior, we're looking for the behavior of the graph as x goes to infinity and as x goes to negative infinity. So in the case of x going to infinity, y is going to go to negative infinity because we have a negative term, because we have a negative leading coefficient on our controlling term, okay? And as x goes to negative infinity, we're also going to negative infinity because this guy is even. For our next one, I don't know, let's call this guy q of x, right? One of the other traditional polynomial names. Let's say we're going pi x to the fourth plus 13x to the fifth plus 7x squared minus 2. And we're not dealing with a fourth degree polynomial, even though that one's written first. This is a fifth degree polynomial, right? Our controlling term is this guy right here, right? A sub n is greater than 0, and q is an odd degree, okay? So our work we did here would tell us that we're following this, right? So then as x goes to infinity, y should go to infinity, which means this part of the graph should be going that way. And as x goes to negative infinity, y goes to negative infinity. So this part of the graph goes like that.